Yeah.
Okay, so we'll continue where we left off yesterday.
Yes.
Yeah, but now we're going to switch
Yeah.
now to water conservation.
The conservation. Yes.
Yes. So when we're talking of water conservation, uh,
Yeah.
in this case, we want to keep water in a place where we can use it. We do not want to lose water or want to increase the efficiency of the water that we have.
Yes.
Yeah. So as we go through the chapter or the unit, uh, in the end, we should be able to identify different methods of water conservation, but
Mhm.
importantly to explain the mechanism with which these techniques help to conserve water. Then in the end, you should be able to understand and carry out a process of irrigation scheduling so that you conserve the little water that you have. So before we go further, we need to understand the dynamics of water in the environment. So as we know, water usually comes to the surface of the earth, usually by rainfall or by irrigation. So in this case, you can have rainfall, which is depicted here, as well as irrigation. So these are the ways in which water reaches the soil. Then when it
Mm.
reaches the soil surface, uh, part of it will infiltrate into the ground, into the soil,
Mm. Mm.
while part of it is going to go as runoff. So
Yeah.
part of it is lost as runoff, then part of it goes into the soil. Then
Mm.
out of that which goes into the soil, part of it is taken up by the plants and is transpired again back to the atmosphere. Then
Mm.
part of it is lost through evaporation into the atmosphere, but part of it is now lost to deep drainage or deep percolation.
Mm.
In some cases, we find that water will rise from groundwater into your root zone. So these are the
Zone, yes.
processes. Yeah, these are the processes that water undergoes as it is recycled from the atmosphere uh, 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 to the atmosphere and into the soil, then back to the atmosphere. So it is important to understand these processes, how they occur, how the process of infiltration occurs, how the process of evaporation occurs, or the process of deep drainage. How does it occur? When does it occur? Then, when you understand those concepts, you'll be able now to say, okay, if I have to conserve water, I have to prevent evaporation, I have to make sure I increase infiltration or I reduce deep drainage. So you need to understand these concepts. So
Mm.
as a water manager, it's important to know where you want to keep your water. Do you want it in the atmosphere? Do you want it in the soil, or do you want it in groundwater? So as we go
Oh.
through, we should be able now to say, okay, this is where I want my water. So what should I do to keep it in this place?
Okay.
Yeah. So
Mm.
we'll look at uh, we'll look at the process of infiltration, because ideally what you want as a soil manager is that when you have your rain, it rains, you want your water to infiltrate the soil, but you don't want it to be lost due to deep
Mm.
drainage, because your crops roots are only in this zone. So you
Mm.
want your water to be in here, in your root zone. You don't want it to be lost by evaporation. You don't
Mm.
want it to, you don't want to lose it by deep drainage, and you don't want to lose it by runoff. So
Mm.
as a water manager specialist, you want your water to be here. So what measures are you going to put in place so that your water stays in here? It does not get lost through evaporation, it does not get lost through deep drainage, and it does not get lost through runoff.
Oh, okay.
So we'll look at the process of infiltration.
Mm.
Yeah, just to understand what it is and how how it can be affected by soil properties.
Mm.
Yeah. So infiltration is simply the process of water entry into the soil. So water entering at the surface at the surface into the soil.
Mm.
So what is important, what is interesting about this phenomenon is that if your soil is completely dry, then you start applying water. The water will be entering the soil very fast. Then
Mm.
with time, as water increases in the soil, it will start to reduce. The rate at which it's entering will start to reduce because
Mhm.
like most of the soil pores now they are wet, and the soil surface as well is also wet. So that the rate of entry reduces. So
Mhm.
initially it's high, then as you continue applying water, it reduces. So with that, uh, so the more pore spaces you have in the soil, the more water is going to be transmitted into the soil. So if you have a higher porosity, the higher the amount of water that is going to infiltrate into the soil. So infiltration has can be divided into three stages. It has three
Okay.
stages with which it occurs. Remember, I said the earlier part is high, then it starts to reduce until
Mhm.
until it will reach a point where it becomes constant. It will no longer
Mhm.
reduce, and that point is what
Mm.
we call the hydraulic conductivity.
Oh, okay.
Yes. So the three stages of infiltration, they will be dependent on two things. First of
Yes.
all, it will be a function of the infiltration rate of the soil. So it will be
Yes.
dependent on the soil and on the supply of water, or the rate of water supply.
Mm.
So if we can look at this diagram here, uh, there's a soil will have what we call the infiltration capacity. So that's the highest infiltration rate a soil can have. Okay.
Mm.
So if a soil we start at its infiltration capacity, the highest, like when the soil is dry, then you start to apply irrigation.
Mm.
Yes. So if that irrigation is the irrigation rate is less than the infiltration capacity, it means
Mhm.
that the rate at which the water will be entering the soil will be dependent on the rate of irrigation. Okay. So
Yes.
is that point understood? So if I would give
Just go through it again.
okay, let me give a metaphoric example. For example, if you eat 3 times a day, okay, that is
Mm.
breakfast, lunch, supper.
Mm,
That's the rate at which you eat 3 times in a day. Then
yes.
if you move from your home, you go somewhere else where they eat twice a day. They just eat breakfast and supper. So
Yes.
where you were, your so you as a person, your capacity is 3 times a day. But because you've moved
Yeah.
to another house where they eat twice, your
Mm.
rate, the rate at which you eat will be determined by that house where you are.
Yes.
So what we're saying that a soil has what we call infiltration capacity, which is the maximum amount of water it can, the maximum infiltration rate that a soil can take.
Yes.
That's the infiltration capacity. But if
Mm.
the irrigation rate is lower than that infiltration capacity, it
Mm.
means that the rate at which water is entering the soil will be dependent on the supply.
Yes.
So if the irrigation rate is two centimeter or 100 centimeter 100 centimeters per second, it means that that amount will be also the rate in the soil, because
Okay.
if you increase the irrigation, the soil can still take it.
So there is a demand and supply.
Yes, something like that. Yes. So if
So,
if there's in this case, the initial stage of infiltration, which we call stage 1, is where the supply is less than the demand. So everything that is being put there will be infiltrated into the soil, because
yes.
the soil is able to get it. So
Yeah.
in the initial stage of infiltration here, which we call stage 1, from here to here,
Yeah.
this
Yeah.
area, it's
Oh, okay.
the rate is determined by the irrigation. So if,
Okay.
for example, this is the rate of irrigation, the y-axis, then the x-axis is time.
Okay.
So if you start at time 0, you start to irrigate, okay, at this rate, at a rate up to here. You keep your irrigation rate constant. You find that as you irrigate, the infiltration in the soil will be equal to the irrigation rate. It will be equal to the irrigation rate. Then you reach a point now when the soil has become wet. Now the rate at which the water is entering the soil will start to reduce. It will start to reduce as the pore spaces are getting saturated. It will start to reduce until it reaches a point where it cannot reduce anymore. So from this point where it can't reduce anymore to the point where it started reducing, this is what we call stage 2.
Okay.
Then stage 3 will be from the time it became constant onwards. And you realize that when it becomes constant here, it means that the pores are saturated. And now you start having water failing to enter the soil. It will start to accumulate on the surface of the soil. And if there's a slope, it will start to run off. So these are the 3 stages of infiltration.
Okay.
Yes. So
V is less than 1. V stands for?
okay. So here we're saying V is less than So the I is the irrigation.
Okay.
So in stage 1, the irrigation rate would be higher than let's see.
I was going to ask, was
No,
both stages?
no. It's
Mm,
actually, both stages were okay. Okay, I think I
yeah.
made an error when putting these ones. So in
Okay.
this, okay, let me see. Okay, so the I is the infiltration rate.
Mhm.
So in stage 1, the V is the irrigation.
Okay.
In stage 1, the the irrigation rate is less than the
Infiltration
infiltration
rate.
capacity of the soil. So
Yes.
whatever you add will just be going into the soil. So in this stage, the rate at which water enters the soil will be dependent on the irrigation.
Amount of what? Yes. Yeah.
Yes. Then as we go into stage 2 now, at this point, when we reach this point, it means that the irrigation rate and the irrigation and the soil, infiltration rate and the irrigation rate have become equal here at this point at time P.
Let's see. Oh, okay. Yes.
Yes. Then from here, when they've become equal now, the infiltration rate of the soil, because the soil has started becoming wet, it will start to reduce. Now, as it is reducing, the irrigation rate becomes higher than the infiltration rate.
Okay.
Yeah, so in this stage 2 now, the rate at which water enters the soil will be dependent on the infiltration rate.
Okay.
Yeah, because now the irrigation can be coming, but now the pores are becoming saturated. It means that not all the irrigation water will be entering the soil. So it will depend now on the infiltration rate of the soil, which is of course now determined by the soil properties. Then as it continues to reduce, it will reach a point where it cannot reduce anymore. Like the infiltration rate to become constant. And at this point, it's a point where the soil, we say the soil has become saturated.
Okay.
And when the soil has become saturated, we call that infiltration rate at that point as the hydraulic conductivity. And
Oh, okay.
yeah, and because now the soil has become saturated, all the pores are filled, the more water you are adding, it will start accumulating on the surface of the soil, because the irrigation rate now is higher than the rate at which the soil can take. So the excess water will start to run off.
Okay.
Yeah, so these are the 3 stages of infiltration. So in this one, so when we reach at this point where the soil has become saturated, yeah, the soil will start to some water will start to run over the surface, and yeah, so meaning that if you are doing irrigation, when you reach this point, you have to stop your irrigation because the water will start to run off. So when we come to the software, we're going to see how we can produce this graph to see, okay, if we start to irrigate, how long can we irrigate before the soil becomes saturated? Then then we'll see how we can be able to explain such kind of phenomenon.
Okay.
Yeah.
So irrigation is equal to KS.
Or in
stage
this
3?
Yeah, so in this stage, infiltration So the I is infiltration.
Oh yes, infiltration, yes, sorry,
Yes.
yes.
Yeah, is equal to the saturated hydraulic conductivity.
Oh, okay.
Yeah,
Okay, yes, okay. It's okay.
yeah, when we reach stage 3.
Mm.
Yeah, yeah. So when you reach stage 3, it means that since at stage 3, the irrigation rate is higher than the infiltration rate. It means that if you're applying 10 units, 10 units of water, for example, you find that only 5 will be going into the soil, and the rest of the 5 will be just running off. But because now we've reached saturated hydraulic conductivity, it means that all the pores are filled up. So any extra water that is infiltrating into the soil is going deep beyond the roots. So when you reach this point, you're losing water, one, via deep drainage and via runoff.
Oh, okay.
Yeah, so when you reach into stage 3, you're losing water, runoff, and deep drainage. Okay.
I think the formula is still okay, Mr. Meat.
There?
In the graph
Okay.
on stage 2, I think it
Uh,
is still okay.
no.
The stage 2 V
So-
is less than I. I think it's okay.
No. So in stage 2, V is greater than I.
Or we need to
Because-
change it to greater.
Yeah, you need to change it to greater because when you're at time P here,
Yes.
V is equal to I.
Okay.
But here, from here now, the I will start to reduce the infiltration rate of the soil.
Okay.
Remember the V, the
Oh no,
irrigation
I
rate?
see. I
Yeah.
see.
Yeah.
Yes.
Yeah.
Yeah.
So in this one, we need to change the sign.
Okay.
Yeah.
I get it. Okay.
Yeah. Okay. So that's for infiltration. Then another process, which is the opposite of infiltration, is evaporation.
Okay.
So if water, remember the first one, we're putting water into the soil via irrigation, it's infiltrating the soil. But now when we
Yes.
talk of evaporation, we have water in the soil, then it's going out of the soil through the surface. So it's evaporating
Yes.
out. So
Yes.
the main driver of this one is heat. So if you have heat on your
Okay.
soil, your water gets warmed up and it changes from liquid to gas, and then it evaporates out of the soil. So
Okay.
3 conditions should be met for the process of evaporation to occur. First of all,
Okay.
of course, you need to have heat to warm the water. So if you have sunlight, it will start warming the water in the soil and the water will start to turn to gas. So the most important thing is that you have a heat supply, which most of the time comes from the sun.
Yeah.
Then as the water starts to evaporate, you know that because as the water is being heated up, it's being turned into gas. Now gas moves from a place of high concentration to a place of lower concentration. So it means that since that water is supposed to go into the atmosphere, it means that the concentration in the atmosphere should be less. So there should be less humidity in the atmosphere for evaporation to take place. So
Okay.
So the vapor pressure in the atmosphere, of course, the humidity should be less than the one in the soil, such that now the gas, the water will start moving into the atmosphere. Then thirdly, for this process to continue, obviously you need to have water in the soil. So if you don't have water in the soil, even if there's a lot of
There's
sun,
nothing.
even if there's a lot of
Yeah.
sunlight coming, there won't be evaporation because there's no water in the soil to evaporate. So these are the three conditions that must occur for evaporation to take place. Yes. So for the process of evaporation as well, it's kind of similar to infiltration in terms of the stages. So if we started from a very wet soil, a soil which is saturated with water, you find that because the sunlight, if we keep it at a constant rate, it means that the water will be heated at the same rate, and the evaporation will start at the same rate because there's a lot of water already in the soil. It will start to evaporate until it reaches a stage now where the excess water in the soil has all gone, the water in the pores. So now for water to escape, it now has to start detaching from the soil particles. Now you remember we said that the soil particles are also pulling onto the water. So you find that you need more energy at that point to evaporate the water. But since we are saying that the sunlight at this point we have kept it constant, it means that the rate at which the water is being lost will start to reduce because the water is held by the soil particles. So at the stage at which the rate of evaporation starts to reduce, that will be our stage 2. Then then it starts to reduce until it reaches a point where now it has become almost like almost all the water has finished in the soil. Then when you reach that stage, you find that the rate of evaporation will almost cease. It will almost be zero. That is that now it means that you have entered the third stage where it's almost there's almost no evaporation. So it has 3 stages as well, just like evaporation, just like infiltration. So when you start dealing with the software, you will know, we will be able to do this at, okay, if we have a certain rate of heat, at what point is the water, because when you're dealing with irrigation, you I'm sure even at Zambia Sugar, you measure the evapotranspiration so that you know if you irrigate.
Yes, we do.
Yeah, if you irrigate, part of the water is going to the plant, some of it is being lost by evaporation. So in doing an irrigation schedule, you also factor in this parameter, the evaporation. Yeah, so this is, when you get there, we'll be able to know and be able to calculate how much is lost by evaporation and how much is lost by plant uptake. Yeah, so
okay.
Yeah, so now that we,
just to take you back there.
Yes.
Just to take you back. Okay. I've seen you've put clay, loam, and the sand,
Oh, okay. Okay.
and they're represented by different dots.
Yeah, different dots.
Just
Yeah.
help me so that I understand. I can be making assumptions.
Okay. Okay.
Is
So
it to show that sand has more drains quicker than the loam and the clay holds more water? I don't know what it's trying to depict here.
okay. So what it means is that
So that is sand,
yeah, this the black one is clay.
is clay,
Then
yes.
yes, then the dotted one is uh,
Sand.
is sand. Yes. So
In between the loam.
yeah, in between there's a loam soil. So
Oh,
yeah, so in a in a clay soil, a clay
yeah.
soil has smaller uh, 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 smaller pore spaces.
And we high water holding capacity there.
Yes, and higher water holding capacity than the sand. So the sand, the pore spaces are bigger. So
Yeah.
when it starts to evaporate, we said that water is also held on the soil particles. So
Yes.
in the clay soil, because they are smaller pores and the particles of clay are smaller, meaning that it has a higher surface area. Or in short,
Mm,
we can say that in a clay soil, more water is held on the soil particles than in the sand.
mm, mm,
So the rate of evaporation in sand, because the water is not held very tightly, it means that
yes.
the rate will reduce fast, because
Mm,
already when you just reach at, for example, here 2 days, most of the
yes.
water would have been, that excess water would have been gotten. So what we are saying
Yes.
that the water which is just in the pore spaces is
Mm,
evaporated faster than the
mm,
one that is held on the soil particles.
okay.
So in a sandy soil, because they are big pore spaces, most of the
Mm,
water will be evaporated by the
mm,
second day. But because in a
no.
clay, most of the water is in smaller pore spaces, and meaning that it's
Mm,
held tightly by the soil, it means that it would take longer for that soil to be removed from the soil, because a lot of energy has to be exerted to separate it from the soil particles.
okay.
Yeah.
No, it's clear now.
Okay. Okay. So that's why you find that your
Yeah.
sand will evaporate fast in the initial stage, and then now
Yes.
it will become almost flat.
Yeah.
Then intermediate is the loam, but the clay will take a bit longer for it
Mm,
to reach
mm,
a stage when it starts to reduce, because the pores are smaller.
yeah.
Okay.
Okay.
Yeah. So now that we've discussed these processes, the way water enters the soil, the way it leaves the soil, the process of infiltration, evaporation, runoff, and deep drainage,
Yes.
we need to now move to the need for water conservation. Why do we need to conserve water? Of course,
Mm,
we have the resource of water is not something which is very abundant. So we can say that we have a limited amount of water that we have uh,
mm,
uh, uh, in the earth, or as a at farm level, for example. And
mm,
because of droughts, you find that the water that you have is less. So you have to make sure that you utilize it, every bit of it, without wastage. So of course,
okay.
because of drought, you have less rain and you have less water that you would desire to have for your farm. So of course, there's meteorological drought. This is when you have less rainfall compared for example, if rainfall this year
Compared,
is lower than the
compared to the
average,
normal.
yes, compared to the normal,
Uh,
yeah. Then you
okay.
have an agricultural drought. This is where you have less amount of water than what the
For the
plant,
crop.
than what the crop requires. Then of course,
Okay.
hydrological drought. This is mostly when you have low levels
Water.
in water bodies. So these when
Okay.
you
I
have
remember that one from the land reclamation.
from land reclamation, yeah.
Yeah, I think you explained those meteorological, agricultural
And
types of
hydro
droughts. Yeah.
okay.
Uh,
Yeah. So
mm,
these ones, they will lead to us having less amount of water. Now, if
yes.
we have less amount of water, it means that we must make sure that this water, we keep it safe, we don't misuse it. And when
Mm,
we come to this diagram, the one that we saw, it means that we have to make sure that when we apply water to the soil, it should just be in here.
yes.
We should not lose it going down. We should not also lose it to go runoff, and we should not lose it for evaporation. We want it to be here so that the plants can access it. So this is going to be the
Yes.
core of this unit. We want the water to be here. How do we keep the water in here? So it can be
Yes.
achieved in
In
this,
the root zone.
yeah,
Mm,
it can be achieved through these ways that we've listed here. So first of all, we have to improve restricted infiltration. So if there's any hindrance for water going into the soil,
yes.
we must improve it so that this water goes into the soil. It does not run off. So as the rain comes, we want all of it to move in. So we need to manipulate the surface of the soil so that the rain goes into the soil. Then, of course, we need to reduce runoff, because if we have runoff, it means less water will be entering the soil. So we have to make sure that we reduce this runoff. Then,
Yes.
when the water enters the soil, we need to make sure that it doesn't go by evaporation. Mean that we have to do something on the surface of the soil so that this water does not leave. But also, as it enters here, make sure we keep it here, it does not go deep. So we have to reduce deep drainage beyond the root zone. Then there are two more
Yes.
things that we can do,
Yes.
is that we can maximize the usefulness of low and erratic rainfall. This one means that if you have, if, for example, in the southern part of Zambia, we know that we usually have
Yes.
less amount of rainfall. So what you do is that you adapt your farming system such that now instead you plant crops that are
Yes.
drought resistant.
Drought resistant.
Yeah, drought that
Okay.
can grow even when there's less amount of rainfall. So that's what this point is talking about. But also, because now we have less amount of
What?
water, we can also do irrigation management. So we keep our
Yes.
water and we know when to irrigate. So we harvest the rainwater and keep it. Then it will be us now knowing, okay, now we can irrigate. Okay, now the soil is saturated, we keep the water. When it becomes dry again, we irrigate, rather than having just the rainfall, because the rainfall, it comes, the soil becomes saturated, the rest of the rainfall is is lost at that time, but you can harvest the water that is going by runoff, keep it, and then use it for irrigation when the soil becomes dry. So these are the measures that we're going to consider. And for each one, there are measures that we can put in place to achieve it. For example, restricted infiltration. What can we do? So we have techniques. Reducing runoff. What can we do? We have techniques. And so on for evaporation and for deep drainage. So,
Okay.
so if we start with improving restricted rainfall infiltration and surface runoff. So we want to increase the amount of rainfall going to the soil and reduce surface runoff. What can we do? The first one that we can do, we talked about it yesterday, is conservation agriculture. So we know that conservation agriculture will add organic matter to the soil because we are not removing the crop residues from the field. So they will add organic matter, and that will improve our structure of the soil. So when it improves the structure, it means that you have more porosity. And when you have more porosity, you have more water entering the soil. Then we also know that because we are leaving those residues on the surface of the soil, as the rain is coming, it doesn't break down the soil. So the rain, that impact, the one which detaches the particles, because there's the cover there, it doesn't break them down. So it means that the structure of the soil is maintained, and the infiltration rate is also maintained. But also because you are not in conservation agriculture, you're not tilling your soil. So again, it means that you are maintaining the structure of your soil. So those who do tillage, they are breaking down the structure and it blocks the water from entering the soil. So that's how conservation agriculture is going to improve the infiltration. But it also reduces the runoff because of the surface residues that you have. Water does not have the leeway to move on the surface because it's blocked by the residues, and it has enough time for it to move down into the soil.
Okay.
Yeah. Then the second one that we can do is that we can have infiltration ditches. So for example, if you have a steep soil, in this case, there will be a lot of runoff. But now for us to reduce that runoff, we just make infiltration ditches where you dig trenches across the slope such that if you have runoff coming through, it goes into these ditches. So in these ditches, it will infiltrate and wet the soil such that the plants are able to access it. But also you have reduced the rate of runoff. You have reduced the rate at which you'll be losing water from your field through runoff. So that's the second measure that we can put in place. Then there are what we call tide ridges, where like you do your ridges, okay, the normal way, but now you start to make these dikes. You block. So what you want is that when you have rainfall, water that is collecting in here does not run off going this direction. So you block it so that it collects in here and then it infiltrates. So you have collected here, it's not moving, it's not running off, but also now it will start to infiltrate into the soil.
Okay.
Yeah. Then
Mr. Miti, on the tide ridges,
Yes.
What type of irrigation system is suitable here, or do we just use these under rainfed?
Yeah, this one
Can we
there.
apply it under irrigation conditions?
No. So for yes, you can put them under irrigation.
So this conservation is strictly rainfall. Eh?
Yeah, this one is mostly for rainfall, because in this case, what we are saying is that we are in places where you have less amount of rainfall,
yes,
or
yes, you are right.
or where you have, maybe when you have rain for today, then it takes.
Yeah, we spoke of scarcity.
Yeah. So maybe if you have rain for today, it takes maybe another week for you to have rain. So what you do is that you want to make sure that the rain that you have, you store it. So in this case,
no, you're right.
Yeah. So
Yeah.
So
Because I was thinking that you should put panga flat.
Oh, okay. Yeah. Yeah. So in this case, we want to keep want to keep the water in the field so that the plants can be using it bit by bit.
Yes.
Yeah. So that's the concept of the tide ridges. Yeah.
Okay.
Yeah. But we can also talk of terracing, where, like, if you have a terrace, you put these embankments or grass strips just at the edges of the terrace. Not necessarily bench terraces, but if you have a slope, you grow like grass strips, or if you want, you can put stones so that you reduce the rate of runoff. So if you are blocking the water here, it means that it will have enough time in this area for it to infiltrate. So if water is moving towards this direction, because of this head, it will not, the rate at which it's moving will be reduced, and it will start to go down into the soil. So we have reduced the rate of runoff and increased the rate of infiltration when we use terraces with embankments. So what we need to understand as well is that the moment you start to reduce runoff, it means that you are increasing the time with which water can infiltrate into the soil. So if we reduce runoff here, it means that we have more water entering the soil. Yeah. So that's for increasing infiltration and reducing runoff. Those measures that we've talked about. Then now we are saying, okay, now the water has entered into the soil. How do we make sure that we don't lose it by evaporation?
Okay.
Yeah. So the first one that we can talk of is surface cover, because remember we said that the sunlight is the one which provides the energy which evaporates the water in the soil. So if we have a cover on top of the soil, the heat which is coming from the sun will be blocked from entering the soil, and now you have evaporation, or evaporation will not be high. So to do this, we can use plant residues, we can use plastic mulch, or we can use the cover crop. So this just this just depicts where you have a plastic mulch, a plastic, yeah. Then also this one where you have a mulch, yeah. Then here where you have a cover crop. So you're just blocking the sun from hitting your soil. And while you do that, plastic. They use plastic, but if you like, on this part of the world,
what stage do they put it before they?
Yeah, so it depends. It depends on the practice. Others, they first put they put it before just before planting.
Okay.
Yeah. So, but where the plant is going to, where you're planting there, you leave a small space for germination. Others, they put them after germination. So yeah. So it now it's a technique where now you have to make sure that as you are putting the plastic, you're not disturbing the crops. But for this
Yeah.
one, mostly it's for high value crops. Yeah.
Otherwise,
Yeah, and you can't cover a
mm,
very big area.
yeah.
Yeah, so that's for plastic mulch. Then this one where I use crop residues, I'm sure this one is the one which is more familiar.
Yes.
Yeah,
Yes.
yeah. So the idea here in all cases is to reduce the heat coming from the sun from reaching your soils. Then another way that you can reduce on evaporation of water is using subsurface irrigation. So
Okay.
instead of using surface irrigation, because the water will be directly hit by the sun and it will start evaporating, you can put your irrigation pipes below the surface of the soil, and then it means that that water will not be directly under the sun, and in that case, the rate at which you're losing your water will be reduced.
Does drip irrigation fall under this?
Uh, it's it's the drip on the surface, no, but there's a where you put pipes below the surface of the
Yes.
ground, yeah, where
Yes.
they are buried. So
Okay.
that one applies.
Okay.
Yes, but when we talk of drip irrigation, it helps to reduce evaporation in the sense that you are only applying where the water is needed.
Yes.
So because when you apply it everywhere, the other soils will, where there's no plant, it will just evaporate.
Yes.
Yeah. So the drip irrigation conserves water because water is only applied to where it is needed.
Good.
Yes. Then we can talk of windbreaks. So windbreaks, these are trees planted in a field to block the wind from accessing your field. So this one, it's used in water conservation because remember we said that for evaporation to take place, the concentration of water in the soil or the concentration of the vapor in the soil should be more than in the atmosphere. So if for example, water is evaporating from the soil, then as it is evaporating, if the atmosphere becomes saturated, it means that
Yes.
the evaporation will stop because there's enough water in the atmosphere. But if you have wind, for example, if you don't have these windbreaks, if you have wind, the wind will start blowing away that vapor in the atmosphere. So if it blows it away, it means that it's reducing the vapor in the atmosphere, and the evaporation will continue occurring. So we are planting these trees so that they don't remove the vapor from the atmosphere here, meaning that this place will remain, will have like vapor. So in the soil, from the soil, the evaporation will reduce.
Mhm.
Yeah, so that's why windbreaks are able to conserve water, because
Okay.
you have less evaporation.
Mhm.
Yeah, then of course the timing of irrigation also, you can factor that one in if you want to help reduce evaporation. So you irrigate when it's cool. So maybe you irrigate in the evenings, such that you have when there's no sun. So it means that almost all the water that you are applying will just go into the soil. Less of it will be evaporated. Yeah.
All right. Thank you. Mhm.
Yeah, yeah. So those are the ways in which we can reduce water loss from the soil by evaporation. But also now we need to make sure that we've made sure that it's not evaporating, but also now we have to make sure that it's not going deep beyond the root zone. So now,
Mhm.
what we need to do is that we need to keep it in the root zone. How we do that? We have to increase the available water capacity. So remember, last in the first chapter, we're talking about field capacity and rooting point.
Capacity.
Yeah,
Yes.
yeah. So we need to increase the what can I say? We need to increase the field capacity so that
Mm.
in short, we need to increase the storage of water in the soil, so that it has enough space for it to be stored before it starts to drip.
Okay.
Yeah. So in that case, what we need to do is that we need to increase the micro porosity. You remember the smaller pores.
Yes. Smaller pause. Yes.
Yeah. So we need to increase the amount of the smaller pores, so that we said that in the smaller pores, that's where water is stored. So
Mhm.
to do that, we need to add organic matter to the soil. When we add
Okay.
organic matter, it means that a lot of particles will be held together, and in the particles being held together, they will leave small spaces between them where water can be stored. So
Mm.
when we increase organic matter, we increase the micro porosity, and we increase the amount of water that is held into the soil. But also the organic matter itself, it absorbs a lot of water. So if you have a lot of organic matter in your soil, it means that it will absorb a lot of water, because it will be like a foam. Because a foam will like hold water to itself. So organic
Mhm.
matter will act like that to hold more water without letting it go. Yeah. So you can use
Mhm.
natural organic matter, or you can use synthetic organic gels. But these ones
Oh,
are,
okay.
yeah, these ones mostly as well, they use them when you're doing high value crops. If you're doing food
Mhm.
crops, you use organic matter, which is more available.
Valuable.
Yeah, so when you add organic matter, instead of the water dripping, it will remain held in the soil itself. So it will not deep,
Mhm.
it will not go deep into the soil.
Mhm.
Yeah. Then the other way is using deep rooted crops. So if you have, for example, in this
Mhm.
picture, you have shallow rooted crops and you also have deep rooted crops, such that when you have water in here, if you lose some water deep into the profile beyond the shallow rooted, it can be taken up by
Mhm.
the deep rooted crops, and it will be,
Crop, yes.
yeah, it will be brought back to the upper horizons.
Yes.
So that's another way in which you reduce on deep drainage.
Okay.
Yeah. So these are the two ways in which we can reduce deep drainage. But if there are any other
Okay.
which you might come across as you research, the main thing, as I said yesterday, is just to know how the mechanism with which it occurs.
Yes.
Then yeah, you can stipulate them as well.
Okay.
Yeah. Then the last one which we talked about was maximizing the usefulness of low rainfall. Yeah. So that one, like I said, you can just match the land use to the soil characteristics. For example, if you have a soil, or you have, yeah, for example, if you have areas where you have dumbos, for example, you know dumbos, where water usually collects.
Yes, yes, yes.
Yeah, so you can utilize those areas for growing your crops.
Okay.
Yeah, so because you know that in these places, that's where you have water, where water comes to settle. So, like for example, when you go to Eastern Province, they are what they call at the Madimba.
Madimba.
Yeah,
Yeah.
I think if you, I don't know if you've been these ends.
Yes, yes.
Yeah, so them, they are utilizing this principle to say, okay, in
Yes.
these places, that's where you have water. So those places, that's why they go to do their vegetables and other crops. So you find that even throughout the year, they're able to produce crops. So they are
Yes.
matching the land use to the soil characteristics.
Okay.
Then we can also use drought resistant crops, like we mentioned. For example, you can use sorghum, you can use millet, which only uses a lesser amount of water.
Yes.
Yeah. Then you can increase the efficiency with which crops utilize water. This now has to do with plant breeding, for example.
Oh, okay.
Yeah, where they breed maybe crops which are able to resist drought.
Okay.
Yeah. Then you can also concentrate rainfall by water harvesting, where maybe you can collect water that's running off the surface of the soil. Maybe you store it in tanks, and then you start using it bit by bit. Yeah, which connects to irrigation now. If you store your water, then now you can be able to use it for irrigation. Because in irrigation now, you are controlling the amount of water that you add. You only add what the plant needs. You are not wasting. So this is how you can minimize, you can maximize the little rainfall that is coming through. So with this,
Okay.
we can zero in on,
So,
yes.
sorry, just per matching land use to soil characteristics. Sorry, I think just go through that one again.
Okay. So this one, what we are saying is that,
Yes.
for example, in an area, for example, let's take for example the Eastern Province. You have areas where
Yes.
you have dumbos. So this is where water does not dry easily.
Okay.
Okay. So for example, if you can have a
No,
place where water collects, it doesn't infiltrate. It doesn't infiltrate as fast as other areas. So you say, okay, we'll be planting our crops in this area where water does not infiltrate fast, such that that water, it will be the one that will be used for the plants to grow. So what you're doing is that you've matched your land use of growing crops to the soil characteristics, because you know that in that area water does not dry fast. So that's where we're going
Yes.
to plant our crops.
Yes. Okay.
Yeah, yeah. So that's
These guys that are growing rice, Kumungu,
yeah.
Western province,
Mhm.
is it part of the example there?
Yes, we can consider it as an example,
They're using.
but
Okay.
but for them it's not. Yes, we can use it as an example where they have matched the land use to that characteristic of the soil, where like okay, they
Mm.
grow it in places where they know that it floods,
Mm.
and you have more water in that place. So it's an example as well. It's a good example as well.
Okay.
Yeah.
What of these guys, the Panapirika, they take the animals in the flats where there's always weight, like
Yeah.
the cows.
Yeah. It's also an adaptation. Like they have matched
Yeah.
the land use of cattle
Yes.
rearing to that
Mm.
place, because they know that in this place
You
water
can't
will
grow
be.
crops.
Yeah, yeah, things
Namuna.
like that.
Yeah. Okay.
Yeah, yeah. So
Mm.
it's an example as well of how you can match the land use to the characteristics of the soil or of the land per se.
Yeah.
Yeah. So having looked at this, we can zero in on two of them: water harvesting and irrigation scheduling, or just we can
Okay.
just say irrigation. So
Okay.
yeah. So for water harvesting, because we are storing water, and when we store water, we want to use it now efficiently, and we are doing
Yes.
this because this is one of the activities which is fast becoming an alternative of rainfall. Not necessarily an alternative, but one way in which we're able to use water efficiently. So,
Okay.
in short, water harvesting will be the deliberate action of collecting runoff and storing it so that you use it for productive purposes. Rather than it just being lost, you collect it and then you use it for growing your crops.
Okay.
Yeah.
Yes.
So the principle is just to capture runoff, then store it, and then make it available to your crops when you have shortage of rainfall or when the soil has become dry. Yeah, so that's just the principle. You collect your 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 runoff. So there are different ways for this one for rainfall have rain harvesting. You find a wide range of techniques. So we won't even exhaust them here, but like I said, the principle is just you to collect water and then use it
Mm.
when it is needed. So
Okay.
there are various techniques in different parts of the world.
Mm.
So
Mm.
we'll just look at a few of them, of which we've already talked about them. So, like for
Yes, I agree.
example, tide ridges is an example of harvesting water, because you're keeping it here and then it's not going anywhere. It will be used
Mm.
for plants.
Mm.
The other one is uh, having water retaining pits.
Mm. Yes.
Yeah,
Yes.
like we said yesterday.
Yes,
Uh,
and days.
yeah, yeah,
Mm.
yeah. So this water will be stored in here, or it will be harvested in these small pits, and then it will be used by
Mm.
the plants. including the retention, water retaining dishes. But also others, another example, I just wanted to show that they can be a wide range. Others just using the roof, the rooftops, they put a gutter, and that water from the roof is going straight into a tank. And that tank is stored, they're able to use it for if it's for crops or it's for domestic use or any other use, rather than it just moving from the roof and then going wherever it wants to go. So I've just put this example just to show that it can be a wide range of
Yes.
techniques. Yeah,
Yes.
wide range of techniques. But
Okay.
if you are going to design a water harvesting system, for example, at watershed level or a catchment level, there are certain things that you need to consider, because effectively what you want is that you want the water that you harvest to be equal to the amount of water that your plants require. Okay, so if what I want should be that, okay, if my plants require 20 liters of water, to harvest that 20 liters of water and then supply it to the plants.
Yes, okay.
Yeah, so there can be a situation where, okay, you are in an area, then you are having an amount of rainfall that is not sufficient for the plants.
Yes.
Okay, rainfall is there, but it's not sufficient. For example, if you need 100 millimeters of rainfall, then in your area you are just having 50 millimeters of rainfall. It means that that deficit of 50, you can
50, yes.
supply it using supplement through
Irrigation.
irrigation. But now what you want now in this case that you don't have, for example, is you don't have an irrigation system, but you have you just have like your farm, for example. So what you do is that you say, okay, your farm, you can, as an example, you can divide it into half.
Yes.
So what we are saying is that if you require 100 millimeters of rainfall, then you're having 50, and you have your farm, which is whatever number of hectares. So that that 50 that you're having is spread across the whole farm. Eh? So what you can do is that you can just cut your farm into half and say, okay, this 50 that is being applied on one half of the farm, we should channel it so that it comes to this other half. So that in that other half, you now have 100.
100, yes.
Yeah, you've understood that. So it means that on that other side, you use it as your catchment area.
Yes, okay.
Then the other one, that's why you use your cultivation area. So the amount of water that you harvest should be equal to the deficit of water that you require on the other side. So what you need to do now is to calculate how much area should I leave for collecting water, and how much, and how much area should I leave for growing my crops. So to do that, you can use these formulas. So the water to be harvested, the volume of water to be harvested, we said it would depend on the area that you have. So if we have an amount of rainfall in an area, for example, in Southern Province, you know that we usually have an average amount of rainfall of this much. when that rainfall falls, you have your catchment area. So when you multiply the area times the amount of rainfall, you get the volume.
Yes.
If you get a volume of water that is that comes to your farm or to your catchment.
Yes.
So out of that total volume, this all volume now you want to channel it to where you have planted your crops. Okay.
Yes.
So this you achieve it by making this water move maybe on the surface of the soil going into the planted area. But because we know that not all the rainfall will run off, some of it is going to infiltrate. Yeah. So we multiply it by what we call the rainfall coefficient. So this is the proportion of rainfall that runs off. So when the rain comes, we said part of it goes to runoff, part of it infiltrates. So the proportion of that total rainfall which runs off is what we call the rainfall coefficient. Yeah. So this is the proportion of this rainfall which runs off. So when we multiply it by, so here we have the total volume, but we know that the proportion which will run off will be determined by the runoff coefficient. So if the runoff coefficient is 50, it means that 50% of the rain that comes will run off. And this is the one which is going to find itself in the other field. Yeah. So we also multiply it by the efficiency. Of course, as the water is moving to your field, maybe some of it will evaporate. So yeah, so not all of it that runs off is going to reach your field. Some of it is going to evaporate. So that is accounted for in the efficiency. So this water now you've harvested it. It has come to your field. So now remember we said that this water that we've harvested now should be able to cater for the deficiency in that area.
Yes.
So we need to find out how much is deficient in that area. So to do that, we need to know the size of our field, which is CA. Then we need to know the deficit. So in this one, the ETC is the evapotranspiration, which we use as an estimate of the crop water requirement. So in short, this is the total amount of water that a plant requires. But remember that we also have rain which is coming, but that rain is not enough. So we are saying that the total requirement minus the rainfall that we have is going to give us a deficit. The deficit. Yeah. So that deficit, it will be, of course, it will be in millimeters. When we multiply it by the area that we have, it will give us the volume. The volume, sorry. So what we want now is that this amount of rain that is coming, that is harvested, should be equal to this volume of water deficit.
Required,
Yes. So what we are saying that water harvested should be equal to the water required. So when we equate this and this, it will give us this formula, such that when you have this, of course, the rainfall, you will know from your maybe past records that we have this amount of rainfall. Then the runoff coefficient as well, you will know depending on your soil type.
Yes.
Then the efficiency is one that you use, you determine as an expert to say, okay, in
Okay.
this area, usually the efficiency is this, depending on the evapotranspiration and other things.
Mm,
Then the crop water requirement, you will know.
yes.
Yeah, so for example, depending on the crop that you're growing, you know the amount of water that it requires. Then of course, again, the rainfall, we said this one, you know it from the past records. So the only two
Yes.
things that will be missing in this equation will be the catchment area and
Area.
the area of your crop. So usually
Yes.
what you can do is that you can make a ratio to say, let me just type it. You can say, okay,
Okay.
you can make, you can rewrite this formula as for example, C over CA
Mm,
equal to equal to this. When you just rearrange it,
mm,
we can say this is equal to this. To this. Okay. Is it
okay.
okay? So I've just
Mm,
rearranged so that this C, this goes down there, and then like maybe just cross, like a cross multiplication.
okay.
Yeah.
Okay.
Yeah. So I've just made I want to know the ratio of the catchment area to the
Catchment and the cultivated area.
cultivated area. Yeah. So in this case,
Yes.
these parameters, you have them, all of them that fall. Okay, let me remove this. It's going to be like this. So all these parameters on your right, you know them. So when you place in these parameters, you come up with a ratio. For example, it would be 0.5.
Yes.
Okay. So once you come up with this ratio, the implication, it means that, for example, if we find that this ratio is 0.5, it means that when you have your area or your farm, which is 100 hectares, it means that 50%,
50-50.
yeah, 50-50, you should
Yes.
grow 50 and then you harvest water on 50.
Yes.
But
Okay.
if you find that this ratio is 0.6, for example,
Yes.
it
Yeah.
means that your okay,
Catchment.
yeah, it means that your catchment should be 0.6 of your
Yes.
cropping area.
So the
Because,
catchment should always be, in a case where, like you said, 60%. So meaning the catchment area should be bigger than the cultivated.
okay, so in this case, let me just do this. If, for example, if we say that we found I'm going to write this one again here. So if we have all those
problem.
parameters, okay, we've placed the values, then we find that this ratio is 0.5. Or okay, let's take 0.6 now. So it means that
Yes.
if I have to know the
Catchment.
the catchment area, it means that this over this. So now it will take us to ratios.
Oh, okay.
That's
Okay.
basic basic mathematics that we did.
Okay.
So if this ratio is 0.6,
Yes.
means that if you are given an area, a total
Like your
area,
example, we had 100. Mhm.
yeah, of 100 hectares. So we are saying that this to this is 0.6. So first of all, what we'll do is that we're going to do this. We're going to say 1 plus 0.6. I don't know if you still remember this mathematics of ratios.
Okay.
It's going to be this.
Yes.
That will be the total. So if this is
Yes.
0.6, it means that if we want to find the cultivation area, it means that it's going to be okay, 0.6. So in this case, because if you want to find the cultivation area, it's going to be 0.6 multiplied by your total area. For example, if it's 10,
100.
if it's 100 hectares, so this will be your catchment.
Up to 60.
Yes. Then if
Okay.
you want to find your cultivation area, it's going to be 1 no, is it? Here we've used no. This is going to be 0.6 divided by
1.6.
1.6, yeah. So it will be like this. Like
Okay.
this, then times 100. Then for the other one, it will be 1 divided by 1.6.
Okay.
Yeah.
Okay. So
Yeah.
we have got 37.5. Okay. All right.
Yeah. So this is times 100. Yeah. So this would be your CA. So the only thing that you have to make sure that you get right is that when you get this ratio, because when calculating this ratio, you can also put it the other way around, where the C is on top, the CA is on top, and this big C is down. Then
okay.
yeah. So what it means now is that when you do it the other way around, it means that this would have been for this, and this would have been opposite.
Okay.
So what it means here is that if you have C over CA, which is equal to 0.6, you can say this one here is 1 over, it's 0.6 over 1.
Oh, okay.
Yeah. But if, for example, here it was 2, if you this one was 2, it means that the big C here is 2, then this is 1.
Okay.
Yeah. So if your answer is 0 is less than 1, you place your 1 below here. So it means that your CA is the one which has 1. But if your answer is above 1, it means that the 1 is, wait, how did I say? If your answer is below 1, it means that this ratio is like 0.6 divided by 1.
By 1, okay.
Yeah. Then if it's no, I think it's even if it's whatever the case, you put 1 on the below.
Yes.
Yeah. Whatever the case, 1 is the one for this one, which is down.
Okay.
Yeah, because if it was 2 here, this ratio would have been 2 to 1. Yeah, if it's 0.6, it means that this is 0.6, this is 1. Yeah. Yeah, so that's how you go about it. So when you find these ratios 2:1 or 0.6:1, you just add them and then find that ratio as the function of the whole area.
Okay.
Yeah, yeah. Or I can just leave this example here.
Yes.
Yeah, I think we can just leave it here then. You
Yeah.
can just simply go through it. So this is
Okay.
where we'll end for today.
Okay.
Yeah, but for next week, like we said, we'll go through an example of this one, the calculation. I think
Yes.
this is the only calculation for this part so far. But tomorrow,
Yes.
when we meet, we'll also do now irrigation scheduling.
Scheduling. Okay.
Yeah, irrigation scheduling. So
Um,
yeah, I decided not to put it here today because it has
it's in the
it's a calculation based, so it needs like to just concentrate on it the whole time.
okay.
Yeah. So for today we'll end here and we'll continue with it tomorrow.
Okay.
Yeah. But tomorrow okay, yachinja kwa program, but
No problem.
yeah, maybe we can do it. I don't know how Sunday is.
No, Sunday is fine for me.
Sunday is okay. Okay. I think we can do it.
Sunday is okay. Kaira hapa na ku church still enda manje 2 weeks watishta ati corona.
Oh, okay. Yeah. So I think we can just
Yeah, this week and next week. Yeah.
oh, okay. Okay. So I think we can just spare an hour. We just go through the irrigation scheduling. Then it means that when
No problem.
yeah,
Sunday will do.
okay. So it means that when we do that, Nishi, we just have the socio-economic aspects.
Yeah, that one aspect is.
Yeah, which we can do. I think that one is not even a long one. Then when we do that one, we just now concentrate on the examples and yeah, the examples and the software.
Okay.
Yeah. So I think we'll end here for today, and then we'll meet on Sunday.
On Sunday.
Yes.
Okay.
Yes.
Now, ish fanyigwira shishita ine manje. Hakuna topic at by Sunday.
Oh, by Sunday. Okay.
Yeah, I've just seen this from the class rep.